I do tokenomics research at Sylo, look at anything to do with the Sylo token and the incentives that are present in the Sylo network. And the idea is to sort of design the network in a way where the incentives encourage everybody to cooperate and to behave in a way that benefits the network as a whole. There's a fair bit of math and economics, and so that's my background. I did applied math and engineering in university. At a very high level, you can think about the internet like this diagram. So over here, we have a device that I own, and over here might be your device. So the devices could be like phones or laptops or servers or any computer at all, really, that's connected to the internet. And if our devices want to talk, the message that gets sent has to follow a path between the other computers on the internet. Essentially, these links just represent which computers can talk directly to one another. So my phone might talk to the cell tower, which talks to some other piece of infrastructure higher up the chain, and then it comes back down to your device wherever you happen to be connected. And so we want to think about messaging on the internet, which is essentially moving some information from my device to your device, or vice versa. The message itself can be a variety of things. So that could be some text that I've typed in, like an IM client, that could be a photo, that could be a video clip or a voice clip. But the key thing is that it's something that we don't want it to be real time. So I'm not talking here about things like a live video call, for example. It's something that can be sent and then received later, and both people don't have to be present at the same time. So most people imagine that when you send a message, essentially that information just moves from my device to each computer on the path between us, and then to your device, and it's done. So it just sort of happens when you hit send, and then that's it. But that's not quite right. And to understand why, it's worth looking at what the problems with this kind of an approach are. The first problem is what I'm going to call the discovery problem, which is essentially, how does my device know where on the network your device is? Finding this route through the different computers, not going down a dead end or not going the wrong way, and eventually reaching your device and actually delivering the content. The thing about discovery that's hard is that devices can change where they are on the network. So if you think of like a typical commute, say, where you wake up in the morning and your phone is on home Wi-Fi, and then you leave the house and you swap to mobile data, which means you change from being connected here to being connected there. And then after a while, you get to the train, and the train offers free Wi-Fi, so you swap to that, and you're at a different place again. And then you get to work, and you're on work Wi-Fi. Devices, particularly mobile devices, move around on the network a lot. And the challenge is that my device at all times needs to know how to get a message to you in order to do this direct sort of peer-to-peer style sending of information. So you can imagine that you might be able to get around this, where every time your device moves, it calls me up or it sends me a message back and says, hey, I've just moved. I used to be at position A, now I'm at position B. You can reach me here now. And that works okay when only one device is moving. But the really hard part is if both devices move at the same time, because then I don't know how to reach you and you don't know how to reach me, and we're essentially just stuck. So that's the discovery problem. The second one is what I'm calling the synchronicity problem. And that is essentially that if you want your messages to be delivered, then both devices have to be online. If you, in an IM chat, you send a message, you get those notifications where it says sent and then received. You can't do that when you're sending messages directly between two devices. There's nowhere that will hold the message in the meantime before it reaches you. You can imagine that a lot of the time this would just cause some delay. So you'd hit send on your phone, and then eventually your partner would come online, your device would come online and would be able to send that message at that point in time. So it would just result in it arriving delayed. But imagine if you had a friend in like Iceland or something, from the perspective of New Zealand, you might never be online at the same time in the worst case. And so you need some way of making it that when your device turns on, if there are messages that I've sent, they're ready to be collected somehow, no matter what my phone is doing, because phones are not always on. That's the synchronicity problem. And so those two together mean that it's quite hard to give the same level of user experience using a peer-to-peer messaging process that you can get from a centralized process. This is what I mean by a centralized process. Rather than sending the message from my device to your device directly, there is a messaging server with a database on it, and it essentially stores messages that I've sent until you come and collect them. So we both essentially meet in the middle of this server, and it hands off information from me to you, storing a copy in the meantime. So if you're currently offline, I would send a message, it would go to the server, it would sit there until you came online, and then you would be able to get the message. That is essentially how a messaging server helps. It solves that synchronicity problem. But whenever you want messages from me, you can ask the server, hi, do you have anything for me? But it also just solves the discovery problem because the server itself doesn't move. If your phone hops to a new network, all it needs to do is get back in touch with the server, which is in the same fixed place all the time reliably, and then it's all working again. So in that sense, there's some really big advantages to this sort of centralized architecture. There's a computer here that's storing a copy of everything we send to one another, and it makes the user experience of communication a lot better. The big downside is that now there's another computer out there owned by someone else that has a copy of our messages on it. Let's get into why this copy of our messages might be a problem. If you aren't paying for a product on the internet, it's likely that you are the product. If you look at any kind of communications company, so I'll take sort of Facebook or Meta as an example, they provide this infrastructure to the user. From their perspective, it's free. You know, what's in it for them? What makes it worth their while? And the key business that most communications companies are in, so social media, any kind of messaging like that, is advertising, targeted marketing specifically. Meta's average revenue per user was about $41 in 2021. And that varies a lot by where in the world the user is from. So I think an American's worth something like $200 a year to Meta on average, which is a lot more than you would probably pay up front to use their services. They're making quite a bit of income off of having your information, and quite a bit more than you would be willing to pay them to actually get access to the social network. So when they provide these communication services, the goal is to get information about you in the process and then use that information to place ads in front of you. The more that they know about you, the more that you are worth. And that's because advertisers are willing to pay more money for an advertising spot if the person viewing it is very likely to buy what they're selling. And this essentially puts privacy in tension. Even if a company that uses this business model promises to, do X or Y in terms of privacy, there is always a financial incentive for them to learn more about you and to make money. Essentially what that means is there's always a reason for them to misbehave. This is essentially why this business model of centralized communications and advertising will tend to invade privacy more over time. Advertising as a business model directly leads to the sort of walled garden phenomenon that we see with big tech, where these big companies are trying to keep you within their own ecosystem. Information about you is more valuable if it's scarce. So if an advertiser wants to reach you to sell, I don't know, again, we'll go with chainsaws. If two different people have the information that you like chainsaws, then the advertiser can buy that information from either party. And so there's kind of a bidding war from the seller of the information that drives the price down. But if a user is only known about by one of these guys, then that's the only way you can learn targeted information about that user. And so these big guys have an incentive to keep you within their walled garden and make sure that they are the only ones who know about you, because that makes you a more valuable user to them. The final aspect of this is that once you've been learned about, once your data is out there, you can't reel it back in. And that's because these advertising companies aren't just placing ads on their own platforms, but they're also selling the data itself. I know that the person with this phone number has an interest in trains. That's a fact that comes from a reputable source like someone like Facebook. That information could be sold on to a third-party advertiser. And then even if you delete your Facebook profile, that information has been pushed out into the world and it's sitting in a different database somewhere else. And there's no mechanism for retrieving that. So it's kind of a one-way thing. The big motivators is like this isn't the only way it could be done. And it's a little weird that it's the default. One common thing that comes up in response to that is there a technical solution? Like, can we just design the system in a way where it's impossible for them to go snooping like that? Still have a centralized server, but perhaps hide the information so that only the people who are meant to be reading your messages can actually read them. That concept is known as end-to-end encryption. The two ends are your device and my device. And encryption is essentially, we're glossing over quite a complicated topic here, but you can think about it as putting what's in your messages inside of a locked box. And that box can't be opened by anybody except the person with the key. So if I put it in a box that only you can open, and then I send it, while it's in the messaging server, while it's on the way, it's locked and essentially just looks like random information, zeros and ones. The messaging server can't understand what it means. But then once it's delivered to your device, you can use your key to turn it back into, hey, what are you up to this weekend? And actually get the content of your message hidden and opaque to you're in the middle. And so I suppose to investigate this idea, like, can you solve this problem with end-to-end encryption? It's helpful to look at a couple case studies. So I'm going to use WhatsApp, which is a chat app that uses end-to-end encryption that's been bought by Facebook. It started off as a startup and then was acquired. And then there's Signal, which is actually run by a non-for-profit entity. So the two of these, I guess, will help us to look at how you might do a centralized system better and what the pros and cons of that might be. So we can jump into WhatsApp. The biggest problem is that even if you hide content of the message itself, so like what's actually being said, there's some information being sent that is impossible to hide. So like the fact that Josh messaged Monty at 5 p.m. on Friday is still information. And if you think about that information added up across all of your contacts, you get a pretty good sense of who knows who, who's close to who, and how likely people are to have similar opinions. Essentially, you know, if you're messaging someone a lot, you probably like them, and therefore you probably have a similar view. So even if you don't know anything about the people in particular, if you've from the metadata, if you have other information about them from sources, you can use that metadata to learn indirectly about the people involved. You can map their social network, and you can say, well, hey, you know, Josh likes chainsaws, so maybe Monty does too, which is, you know, usually correct, at least for certain kinds of thing. So there are ways for these to make money off of your data, even when the message content itself is encrypted. And WhatsApp is also a good case study to look at because it shows an example of this sort of privacy backsliding that I was talking about. So when the acquisition was made, WhatsApp was a privacy-first company. You know, it made its brand off of the end-to-end encryption and security side of things. And when the acquisition happened, Facebook essentially promised that the metadata wouldn't be shared for advertising purposes, and that essentially didn't happen. I mean, there's a lot to read about this. You can look it up if you like. But in 2021, there was a bit of a scandal in terms of how that data was being used, and a bunch of users quit. And in fact, a lot of them moved over to Signal and Telegram and a variety of others more privacy-focused messengers. But ultimately, it didn't end up being the death knell of WhatsApp. You know, it's still popular today, and lots of people still use it. In that situation, somebody at Facebook probably made a calculation and said, well, hey, the extra money we make off of all of our users is worth losing, say, 5% of our users over privacy concerns. So we still make money overall. And they've found it profitable to go back on their privacy promises. And I guess the thing is that they are always able to do that because the software is centralized. So if you have a server with all of the messages on it, that sort of thing is always possible because they can just change how the app works and how the system works. Decentralized systems are often harder to change unilaterally like that, which is one reason that they tend to be more appropriate for privacy. Yeah, essentially, if the users don't vote with their feet, then you can expect privacy to continually stepping backwards, so long as there's a profit motive involved. And that brings us to Signal, because in my opinion, they're actually quite a good solution to this problem. They remove the profit motive by being a non-profit organization with a charitable purpose of privacy. So they say, yeah, we technically could read your stuff and collect your metadata and so on, but nobody can acquire us and make money by doing that because that would be illegal because of our charitable purpose. And so the legal system essentially says that you can trust them because if they stop acting in the interests of privacy, then they can get sued and so on. So that in a lot of ways helps. You know, it means that they don't have this incentive to go snooping anymore. But the question becomes, can an app that's built in that way and with a charitable purpose compete in the mainstream against an advertising business model? So Signal is doing very well. You know, they've got 40 million active users, free to use with donations if you to support them. But the key thing is that the more users they pick up, the more that they have to spend on their servers and services and so on. And they've probably picked up most of the keen privacy advocates by now, the ones who are willing to donate and support them. So the question is sort of, could you do the whole thing this way? Could you make everything work in that manner? And is that the way to solve the problem for everybody, or is it just a good option if you particularly need privacy? What would be ideal is if everything were to have this privacy built in by default, so that people could choose to give away their data to use apps or not, up to their own preference, and it wouldn't really matter whether the app you picked was privacy focused like Signal or not. It seems at least a little bit risky to bet that the Signal Foundation will be around forever or something like them. You know, it doesn't seem like a future-proof solution. How do you design a network where the user's data is under their own control? How can you make a business model around that network that brings it to market at scale without compromising privacy? And how do you make it long-term sustainable, even as the people who operate the network might change? Those are the goals that we're trying to achieve and the problems we're trying to solve with decentralization. What we're talking about today is the opposite of a centralized communication system, which is decentralized communication systems. And we're just going to look at what's out there. What are the other alternatives to doing it the centralized way? And hopefully with that context, that'll help us to understand why we're doing what we're doing with the Sylo nodes and the Sylo network and with the seekers, and help to explain why a lot of the more complicated stuff that we're doing is necessary. A bit of a recap. Centralized communication systems have a server in between the two people who are communicating. And that server stores a copy of all of the messages that travel between those two people. The thing about that is that copy contains information about the pair of you, and that's useful for targeted advertising. So the company who owns that server can use that knowledge about you to make a profit. And that creates a profit motive for intruding in your privacy. The business model of these centralized systems, that's the fundamental problem. The fact that they're centralized just allows them to take that look into your information. So you can sort of address those kinds of concerns with technical measures, things like end-to-end encryption. For example, WhatsApp and Signal both use that, and that helps. But there are other ways these companies can still monetize the information that they know about you, even with end-to-end encryption. So that's not a silver bullet. That's not like a perfect fix. And so basically where we got to last time was that if you wanted to solve this properly and not have this situation where there's this profit motive to invade people's privacy, you'd need a system where users' data was under their control. You'd need a system that had a business model that let it scale up to the mainstream. And also you'd need to be confident that there wouldn't be an external pressure to change that business model in the future. So it would need to be sort of a sustainable way of providing the service to people that wasn't vulnerable to like a change in ownership, for example, of the company that was doing it, which is a bit of a tall order. This is quite a tough challenge. That's kind of what's wrong with the centralized approach. And so today we're going to look at 3 different other ways of doing comms with the goal of understanding their pros and cons and why they might not be complete solutions either. Areas that we're going to talk about are the 3 sort of categories of decentralized system that I'm going to talk about are federated networks, pure peer-to-peer systems, and then something I'm calling decentralized services. It kind of builds upon both of them and fills a little niche as we'll see. I'm not claiming that this is like an exhaustive list. This is more like illustrative of what kinds of things are out there. So there's going to be tons of projects that I don't mention, tons of really good work that's not in this talk just because of time. And I probably should add as well that the projects that I do focus on, I've picked largely because I think they're good examples of what they're trying to do. So even though I'm going to be kind of critical of things here, that's not necessarily me saying they're bad. That's just like, looking at them and saying what's good and bad about them, trying to understand them more deeply. If you've got a centralized server that's doing messaging, maybe for the sake of example, we'll talk about Facebook here. You've got the Facebook server that stores all of your posts, all of your photos in one centralized place. A kind of natural way to think about improving that is rather than having one server, you would sort of break up all of the work that the Facebook server is doing and spread it out among multiple different servers that are owned by different people. That's what's called a federated network. So anybody who wants to join in can run their own little server, or quite big server, depending on what you want to do, that provides all of the same services that a centralized server does. These servers cooperate in order to provide the same kind of experience that something like Facebook does. So I'm going to zoom in on a project called Mastodon as an example of a federated network, but there are some others like Diaspora. There's a variety out there. And so the key thing is that each user chooses their own server when they sign up. So both Monty and I might be part of the Mastodon network, and we would both host servers. And then if you wanted to be part of Mastodon and see posts on that Mastodon network, you could choose to either sign up with Monty's server or mine based on who you like best, like who you trust the most, who has the best record for, privacy or reliability or all of those sorts of things. And whenever the servers try and show you some content, like for example, a feed, my server and Monty's server work together to provide that to you. Often when you want to see something on a social network, it'll actually come from a lot of different servers. And that just depends on where each of the friends of yours that you're getting posts from have their information. So that's a little abstract, a little high level. So let's get a bit more concrete. So if we think about like a Facebook feed, or in this case, a Mastodon feed, with Facebook, you would send a message to the Facebook server and say, hi, send me a list of posts, please. I want to see my feed. And that one server would do some thinking, figure out what to show you, and then send back a list of stuff to look at. That's fairly simple. With Mastodon, it's a little more complicated because the data that you want to see isn't in one place. It's spread out. If Monty and I used different servers, then if I wanted to see Monty's posts, my server would have to ask Monty's server what she has posted. And so there's this sort of cooperative process where I'll ask for the feed. So I'll say to my server, hi, could I have the feed? And then my server will coordinate with the other servers and collect everything that's relevant to what I want to see and get all of the posts that are visible to me and have the right permissions for me to see them. And then once my server has all of that information, it can then sort and organize them and figure out which ones are relevant to me. So this is where things like curating your feed might happen. And then finally that curated feed would be sent back to my phone. The key thing here is that if Monty has set a post as private and her server is being good, then it just won't send my server that post because I don't have permissions to see it. If Monty trusts her server, then all of her private content stays private. And the idea with a network like this is that people will be able to choose their own server, and that'll mean that the trustworthy servers, the ones that are effective at keeping things private and not taking advantage of users, they'll become more popular. That's sort of the overall idea. And so there's a couple of good upsides to a system like this. Each server can only see a fraction of all of the user's private information. At a fundamental level, it's better for privacy because even if the server was completely nefarious, it just wanted to monetize everything, it would simply be able to see less in total. And also because users can switch server, you would expect that the bad ones would lose users and the good ones would gain users. So there's sort of this competitive situation where they're all trying to convince people to work with them essentially to store their posts on their server. And that networks like this also come with the option of bringing your own server. So if you're really concerned about privacy, you can start and run your own Mastodon server, which means that you have full control over the computer where your data is stored. So if you're really privacy centric, you don't need to trust anybody else, so long as you're willing to pay the costs of running a Mastodon server for yourself. And then you can participate in that wider social network, but also know for sure that no one else is going to have access to your data. And in that sense, it's a really good solution. But where it gets sticky is when you try to think about what would happen if everyone used Mastodon. Can this actually ever replace something like Facebook? The essence of it is that bringing your own server isn't easy to do. You need to be fairly technical. And there's also costs associated with it because you basically have to set up and host a server on your own computer or pay for something like, Amazon Web Services or Azure to have a virtual host somewhere in the cloud for you. Most people won't do that. That's a fair bit of hassle. And so fundamentally, people's data will still be out there under someone else's control. And if you imagine that this all scaled up to be the whole world and everyone is using Mastodon instead of, say, Facebook, those individual servers that people are using would have the same profit motive that the one central server does in Facebook's situation. So in that sense, it's not a perfect fix. In practice, most people who use Mastodon actually sign up with the default server, and Mastodon, a non-profit, provides that. So that's good, you can probably trust them. But again, it's that scalability concern from last time, like with Signal. If every user is a cost to the Mastodon non-profit, can this become a big mainstream competitor to the advertising-driven business models of the mainstream services? And then I guess the third point is going to be useful for later. The Mastodon servers do a lot of heavy lifting on behalf of their user. So they store every post, like every image, every video clip, permanently forever. And then whenever anybody asks to see that stuff, their job is to serve it out. So they have a fair amount of storage costs, bandwidth costs. Basically, the cost per user for a Mastodon server is quite high. that's a factor that limits their ability to scale when they have this non-profit situation going on. I guess that sums the federated network options up. They've got some advantages, but they're not a silver bullet. So we've talked about the federated networks. Let's compare that with pure peer-to-peer solutions for messaging. So we've already touched on these. We talked about them in part 1. And I think today what we're going to try and do is maybe go one step deeper and talk about some of the potential solutions that you can apply within a peer-to-peer context. So if you were sort of saying, I'm only going to solve this in a peer-to-peer way, what kind of clever stuff can we get up to make peer-to-peer better? So essentially, peer-to-peer just means that there's no server in the middle and the two devices communicate directly over the internet. As we talked about last time, they have a couple of fundamental issues in terms of user experience. So those are the synchronicity or sync issue. There's also discovery, which is finding other peers. And then there are some implementation concerns for mobile devices that we're going to talk about too. It's worth reiterating though that peer-to-peer is fantastic in the sense of privacy because all of your data is kind of mastered on your device. And so it's fundamentally in your control. Also, if you want to send a message to a particular person and you know who that person is, you can encrypt that information so that only they can read it. So even though you might have to send information across a network and someone else could potentially look at it, the fact that you know who the recipient is, you know which peer you're sending it to, means that everything can be kept private, even though that message might follow a route involving multiple other computers. From a privacy perspective, it's great. It's just that we have to solve these technical issues. So we'll look at each of these in turn now, along with one way that you might solve it within a peer-to-peer context, and we'll see how that looks. The first one we're going to talk about is the sync problem. So this is essentially, in order for information to move between two peers directly, they both have to be online at the same time. So if I was going to send a message to Monty using a peer-to-peer protocol, if Monty's phone is off, I can't send a message and kind of leave it for her to read later. She's got to be online and her phone has to be listening for messages coming from me, otherwise they just won't get there. There's nowhere to sort of store them in flight. And so that's basically what a server provides, is a place to leave messages for someone else later. But you could also try and solve this a different way using just the peers in the network. And one solution using that is something called a gossip protocol. So that basically works like this. If I want to message Monty and she's offline, I might know other peers who also know Monty. Maybe we have like a bunch of mutual friends in common, if we're using like a social network example. And I know that if I send a message to Monty via one of our mutual friends, that person can also deliver it on my behalf if Monty and the mutual friend happen to be online at the same time. So now any one of us can be online and Monty will still get the message. So I might send my message to Monty through 10 different mutual friends. And then if any one of those 10 are online, my message will get delivered when Monty pops up, when her phone comes back on. That would essentially solve the sync problem because from Monty's perspective, that message is waiting and ready for her when she comes online. And from my perspective, I can send it and then forget about it. And I can just trust that it'll get there at some point. And this largely works, but there are two key downsides to it. The first one is that you have to rely on these other peers to behave altruistically towards you. They have to do something for you, basically for free, in order for this to work. And so it's not entirely for free because there's kind of a tit for tat thing going on. You have to do someone a favor one day, they'll do you a favor the next day. So this isn't like a fatal problem, but it does mean that certain kinds of application don't really work this way. So if you ask someone, hi, I've got like 500 gigabytes of video that I want to send to Monty, most phones aren't going to be able to do that. And they're definitely not going to want to because that's your entire data cap going for a month. There's limits to what people will freely share, and that limits what you can do with this kind of tech. The other thing is that it's from a sort of bandwidth perspective, it's quite inefficient because if I could send this message through a centralized server, I send it once to the server and then again to Monty's phone, and that's sort of 2 hops. But then if I'm using 10 peers and any one of those 10 can deliver it to Monty, that's 10 hops, or plus 1, I guess, whoever sends it to Monty first. And so it's almost like 5 times less efficient to do it this way overall, which not the end of the world, but it's worth knowing that these things are often less efficient than a centralized approach. Yeah, so that's the sync problem and how you might tackle it. with a purely peer-to-peer mindset. The next problem, and this is one we've also discussed last time, I'm calling the discovery problem. And so this is essentially, how do peers know where to find other peers on the network? So mobile devices move. Like if you think of a normal commute, you'd go from your home Wi-Fi, you'd go to data, maybe your train offers Wi-Fi, back to data, and then the office. And so over that hour, you're in 5 different network locations, which means that it's often quite hard to know where to send a message across the internet. And that's illustrated here. You can see that the device used to be connected along this route, but now it's connected along this route here. The fundamental issue, the one that's very hard to solve, is that if both peers move at the same time, they have no way of getting back in touch with each other. If only one of them moves, they can sort of have a chat and figure it out. One can message the other and say, hi, I've moved, you should update where you think I am. But when both of them move together, they can just lose touch completely. And the related problem is when a new peer joins up for the first time, it doesn't know how to talk to anybody because it has no other peers that it knows the address of. And so there's a lot of technical solutions to this. I'm just going to touch on one of them. And so this idea is a discovery server. So each peer can publish their location to that discovery server for anyone else to look up. So you can almost think about putting like a post-it note up on a bulletin board, or putting your phone number in the phone book, something like that, right? And then anybody who wants to know where you are just needs to look you up in that address book. And because this is a server, every peer knows where on the network that server is, because it won't change. So the server can just say to everybody, hi, this is where I live. If you need to find out where somebody else is, come ask me. And this discovery server essentially solves this discovery problem. Because if I lose track of Monty, all I need to do is ask the discovery server where she is. And then once we get in touch again, we can go back to peer-to-peer. So the only thing that my device is getting from the discovery server is how to reach Monty. We're not relying on it for storing anything sensitive like message contents. It's just about putting us in touch. And so in that sense, this is quite good for privacy, because it's taking the centralized server, but it's using it for only the part that needs to be centralized, as opposed to just storing all of the data in one place. That's one way you might solve discovery in peer-to-peer. The main downside with this, again, comes with scaling. Somebody has to run this service and spend some money to provide it to the network. And so you again sort of come to this question of altruism. Could this scale up to encompass the whole world? Who would pay for the servers? How would you make sure they were reliable? All of that sort of thing. That discovery server would know some metadata about you, because it knows who is trying to reach who. So it's almost a perfect solution, but there are still some privacy aspects to it, although we're not really going to get into those. But I think the third issue with peer-to-peer, and honestly the most challenging one from a sort of practical perspective, is what I'm just going to summarize as implementation issues. The way that mobile devices work, like the operating system, isn't very friendly to peer-to-peer applications. So the basic assumption that a phone operating system makes is that apps are only really active when they're open, like when they're being actively used by the user. And there are some good reasons for that, like phones have limited battery life. So you sort of want to be able to tell apps not to waste battery when the user isn't using them. But what that means is you often can't write an app on a mobile device that can passively participate in things like gossip protocols in the background, because the OS will say, hey, why are you using resources? That's not cool, and just shut the app down. And they don't really, protocols like that need to kind of be passively online so that stuff can happen and they can hear about it. A gossip protocol doesn't really work if the app is only running when it's open and in the user's hand, because that's such a small fraction of the time. There's also something called network address translation, or NAT. And this is honestly a little bit out of my depth, the technical detail. But basically, the kinds of networks that mobile devices are part of when they are outbound data on your phone, roaming networks, that sort of thing, they can choose what kind of traffic is allowed to reach your phone. They tend to just disallow the kind of traffic that peer-to-peer software needs. So it can often be quite hard to actually get the address of a peer going through a NAT process, depending on the network that your phone is on. And so when you take these things together, apps that can ask a fixed address, like a central server, for updates, work much better with mobile phone devices than these sort of peer-to-peer style apps that are always running and need to be able to reach peers directly. And what this means is that the user experience can't really compete this sort of more centralized design, in part because of the way that the operating system is set up. So that was a lot of sort of bits and pieces of sort of disconnected information. So maybe we should try and draw some common threads out of this and see what we've learned. The fundamental thing is having your data on your device is the best for privacy. You have the most control in that situation. But as we've seen with these peer-to-peer examples, there are some problems with how software works that you can only really solve well with the server. But as we saw with that discovery server example, you don't need to do everything using a server. And you can design services, small kind of utilities that solve the problems with peer-to-peer in kind of a minimal way. And if those services do nothing else, and they only focus on that problem, you don't need to spend a lot per user to offer those services. And also, by design, leak very little information about the user who is using those services. And so this sort of leads into the third category of decentralized communications tech that I'm going to be talking about, which is decentralized services. If you design these services right, you can basically do peer-to-peer plus, where most of the user experience problems of peer-to-peer are solved by these services. And it means that you get, you can have your cake and eat it too. You can get the best of both worlds here. You get both user experience and privacy. This category of decentralized tech, there's a lot of examples of it throughout the space. And there are also some of the most technical things you can read about in decentralized comms. They're sort of the furthest from what people normally experience when they use the web. So rather than getting into a full analysis of what's available with these, I thought I would just deep dive into one of them, which is sort of a precursor to the kind of service that we're working on at Sylo. So we're doing something in this category. And what I'm about to show you isn't exactly what we're doing, but it's something that will help you to understand what I will explain in future talks, which is what we are doing. It's kind of the first half of the story there. So here's an example of a decentralized service that will effectively help to solve those peer-to-peer problems. And I'm going to call it Event Relay. The way that this works is does exactly what's needed to move information between two devices using a central server and very little extra. And in doing so, it solves some of those problems. So let's just walk through what happens when an event relay is done. So the situation we're in is Monty's device over here, Monty's phone, wants to send me a message, but I'm offline, so peer-to-peer directly won't work. And so essentially, Monty can package up her message into an event, which is the thing that's going to be sent through this relay service. And in that process, she also encrypts the event so that only I can read it. So even though it will be on this server in the middle for a period of time, it's opaque to that server. It's just zeros and ones. Once Monty's done that, she hands the event over to the relay service provider. She says, hey, this is for Josh. Please hold on to it for me. And she goes offline. So that's the end of Monty's involvement in this. Sometime later, maybe like an hour, maybe a day, whatever, my phone comes online, and I want to know what's happened. So I call up the event relay service and I say, hey, are there any events for me? What's happened? And the event relay service has this event from Monty, so that's passed on to my device. Because it's for me, I can decrypt it. And so now I have the information that Monty sent me. I've got the message. And now that I've collected it, the event relay service, it doesn't have to care about that event anymore. It knows that it's been delivered, its job is done, and so it can basically just delete that event. And it may as well delete that event because it's meaningless to the relay service because of that encryption. So all this really does is stores kind of in-flight messages. And so you can imagine a peer-to-peer app that might use this service where it first tries to reach me directly. So Monty's phone would try and establish that direct connection with my device. But then when it can't, it falls back on the relay service and says, I tried to reach Josh, but I couldn't. So please pass this on to him when you get a chance. And that'll mean that no matter whether or not I'm online, from the perspective of my user experience, either way, I turn my phone on and Monty's message turns up. It just happens to go through a different route. So this is an example at sort of a high level of what I mean by a decentralized service. And yeah, like I said, this builds into the incentivized event relay that's talked about in the white paper, but we'll get there next week. So in a little more detail, this event relay solves the sync problem. If Monty goes offline after the message has been sent, it still gets through, so tick. Event relay also solves the discovery problem, because even if Monty loses touch with me, like she doesn't know what address my phone is at, she can leave an event with the event relay service that says, hey, you can reach me at address XYZ. You can find me here. Monty knows where the relay provider is. I also know where the relay provider is. So even though we don't know how to find each other, we can both find that midpoint, and that lets us reestablish peer-to-peer contact. So in that sense, this is great because it gets us through those user experience problems while also giving us the data privacy benefits of peer-to-peer. I suppose the main thing here that we still need to think about is that we're still relying on someone to provide that event relay service. There's bandwidth being used, there's data being stored, a computer's running somewhere that needs paying for. Someone's got to provide that service, and we need to think a little more about who they are and why they might do that if we're really going to scale up to the mainstream with technology like this. In particular, we need to think about why they're motivated to provide that service, why they're motivated to make that service really reliable, because centralized communication is very, very reliable, and you need to be able to match that with a decentralized approach if you want to compete in terms of user experience. And finally, as well, you need to make sure that the availability of that service will scale. So if the network gets twice as popular, you need twice as many event relay service providers, and you need a mechanism for making those two line up so that everyone can still do their thing when the network grows. And these questions lead into the ideas of incentivization that we're going to cover in the third and fourth talks. There's a fair bit there, so I would recommend watching them to get the most out of this one. But if you haven't already, basically they explored the different ways that you can do communications between computers, messaging or calls or anything like that, social media, all of that stuff is broadly communications. We were exploring how peer-to-peer communications were very good for privacy, but they have some user experience problems that you can solve with something called a decentralized service. One of the issues is that somebody has to be willing to provide that service. So today, what I'm hoping to look at is recapping that idea of decentralized services in a bit more detail, and then understanding how we can encourage more people to provide that service so that peer-to-peer apps can be as good and high performance and have a good user experience as their centralized alternatives, so that they can compete on a level playing field. So yeah, we're going to be talking about system design, like the design of these decentralized services and the systems they work with. And also we're going to be talking about incentivization and sort of the decision that people make when they want to run one of these services and what the pros and cons might be, the sort of trade-off that they're making. So I'll start with a bit of a reminder of the specific decentralized service that we talked about last time. So we introduced this idea called event relay. And this is essentially an extra component to a peer-to-peer system that solves exactly the issues that peer-to-peer messaging faces and nothing else. So it does sort of the bare minimum required to make peer-to-peer work well, without compromising privacy and without storing any information about you permanently. So this sort of works by having, rather than a centralized database of all of your information, like the history of all of your Facebook posts, all that the event relay service stores is messages that are sort of in flight. So they're between the sending device, in this case Monty's phone, and my device. And again, recapping, the reason that this is good is that it solves two problems. So there's the issue that Monty and I might not be online at the same time, which is called the sync problem. So essentially the messages that are in flight can just wait here in the center until I turn up. And they also solve the discovery problem, which is about Monty's device and knowing where on the network my device is and being able to actually get those messages to me. So in that way, this service gets you to this sort of peer-to-peer plus kind of system, which has all of the performance of the centralized approach, but also is private and secure and all that good stuff. So that's why this is cool. We're going to talk about this decentralized service specifically, but a lot of what I'm going to say applies to more broadly to any kind of decentralized service that you might think about, other projects as well. So it might be a useful lens for understanding those. We don't need to worry too much about the details yet, but we might get into those. And the thing that we have to think about now is that somebody has to provide this service. Someone has to say, I'm going to set up a computer that's going to be running this service, and it's going to be listening for messages from senders, and it's going to be waiting until receivers turn up to claim those messages. So in order to provide this service, there needs to be a computer that's on and sort of active and listening and ready to communicate with anybody who shows up. A human has to organize that. They've got to pay the power bill or rent that computer, and then they've also got to maintain it and make sure that it's working and keep an eye on it, essentially. We can look at those service providers, the people who are running this service, and think about what motivates them. There's plenty of decentralized services out there that work quite well based on people voluntarily doing this for the good of the network. And so if we understand why those systems work and what motivates those people, we'll have a useful way of thinking about how to grow a network in general, right? Understanding the motives of these people leads us to a good way of thinking about scalability. The main two reasons that you would want to do this are basically selfless. They're sort of altruistic, good for the community, good for the world, good vibes kind of reasons. People do this because they realize that they're enabling other people to communicate privately and achieve the goal that the system they're part of is achieving. So maybe if we take a separate example to messaging, people who are seeding on BitTorrent might be an example of people who are providing that service. You can use this lens on a bunch of different systems, but the common thread is that they're generally wanting to make the world better for other people, and they also like the idea of contributing to something like a community or a vision that's bigger than just them and what they're doing. And those are pretty powerful motivators. But the trouble comes that there are also concrete costs associated with doing this. So again, in order to run that service, you either need to own the computer it's running on, or maybe rent it off of like Amazon Web Services, something like that. And then on top of that, you also need to keep an eye on the service and make sure it's still running correctly. So that's a time cost. These factors kind of trade off in the heads of the people who are thinking about running these services and enabling these systems to work. You can sort of understand this as almost like a scale. So if this is the fulcrum that it all balances on, every individual has something like this going on inside their head, whether or not they're actually providing the service. So they're thinking about doing it, and they go, well, these are the good things, the world will be better, I'll be contributing to the community, and they're weighing that up against the costs associated with that. And depending on the person, they'll tip one way or the other. So every person is going to have different weights on each side of the scale, different technical backgrounds, different financial situations, outlook, all that sort of stuff. But any person can be sort of thought about in this way. It's just a matter of how important they rate each of these components. And so it sort of follows from that if we want more of these decentralized services to be running, we've got to influence this weighing up of the options, right? This trade-off. We want to make it so that things tip to the left on the screen and this side wins out, because then more people will provide the service and we'll be able to do private communication at scale using these decentralized services. And so to do that, we are going to use the idea of incentives. So this is a concept from economics, and you can define it quite formally, but I think the simplest way to sum it up is that it's about changing the trade-off. It's about changing this balance by either adding benefits to this side or removing costs to that side, from that side, so that it's a better deal to do this one. The goal of incentives is to change people's behavior by changing how they feel about the decision itself, right? You want to make it better for them to do one thing than the other. And so incentives can be done in two ways. So let's take an example. Maybe we want to reduce the number of cars that are parking in the city centre. You could try and incentivize less parking by giving out vouchers for public transport. That would be a positive incentive. Or you could fine people for parking, or maybe increase the parking costs of parking on the street, right? And that would be a negative incentive. It's important to notice with the negative ones that even though there is a cost attached, people don't have to pay that cost. So often, for example, parking on like dotted lines where it's illegal to park, the fine acts as a deterrent and very few people end up paying that fine, but everyone's behavior still changes. So you don't necessarily need to be penalized by an incentive for that incentive to change your behavior. If you know about it, you can sort of plan around that, and it all ends up working out. That's like an overview of incentives from sort of a theory perspective. What we're going to get to next is applying that to event relay. So with event relay, what do we actually want to incentivize? What's the outcome that we're trying to achieve with these incentives? And I suppose the key thing here is that this node has to be quite reliable to actually improve the user experience of a decentralized app. So this sort of works by Monty sending that message, and it's holding and waiting here for a while before I eventually arrive and collect it. If Monty tries to send it and the service isn't online, then this doesn't work. And if I try and claim it and the service isn't online, this also doesn't work. The performance of this node, of this relay service node in the middle here, ends up being very important to how effective this service is at improving the user experience of a peer-to-peer app. It's not enough just to incentivize people to have and run these nodes. We also need to tie the incentives directly to how well they're doing their job, so that you get this decentralized infrastructure that's highly reliable and useful that apps want to build on top of because they know that they can trust it. And that ends up being to everybody's benefit, because if the network's reliable, then it gets a lot more traffic, and this is sort of virtuous cycle going on, which we'll get into more detail about. So in particular, we want to incentivize the relay service to be high performance, and you can quantify that in a bunch of different ways. There's the concept of uptime, which is just what percentage of the time can you actually reach the service across the internet. If the computer was off, then it wouldn't be online, and so it's just about how much the service is online. It's important that even when there's a lot going on, the service is responsive. Like if it takes 10 seconds before your message reaches the front of the queue that the service is holding, because there's lots of other traffic, that's also not very good. So it needs to be quite responsive. The service also needs to have high throughput so that it can help out many different senders and receivers at the same time. That's desirable. And because this service is storing in-flight messages, it needs to store them for long enough that they get claimed. Like maybe my phone's off for a couple of days. It's good if that message is still there even after a couple of days, rather than like the service deleting it after an hour. So these are all aspects of how the service works that you want to be able to directly reward when the service does it well, so that it ends up providing that good user experience. And then other than these technical performance goals, you want the incentives to allow the network to scale. You want supply and demand for the service to automatically balance. So that means that when more people demand the service, it's a better deal to supply it, essentially. You want there to be this nice link between the number of people who are willing to help out and the number of people who want to use the service. Finally, there's this idea of longevity. So because we're trying to make a decentralized service here, it's really ideal if the service is essentially, it doesn't really matter who's providing it. So each provider is more or less interchangeable with the others. And if you design it in that way, it means that you could have a completely different set of individuals providing the service and everything would still work. You don't have any kind of dependence on its current participants. And I think that's an important property for decentralized systems, is because they need to include anybody and everybody, they have to work like that. You can't have anyone in a privileged position with more responsibilities. Yeah, so those are the goals of incentivizing this service. That's what we're trying to achieve. This is where things get a little more technical, and I've tried to keep this talk at a fairly digestible level, with the real details coming in the fourth one. I think first what I'm going to do is describe the incentivized version of event relay, and then we can talk a bit about the why and the how after that. So essentially what happens here is the sender is providing compensation for the service to the node or the service provider in the middle. This is actually harder than it seems, because the sender and the node don't know each other. They're two computers on the internet, complete strangers, and they have no particular reason to trust one another. And so you run into all these problems where if you wanted to be a bit cheeky as a sender, it's easy to design a system where it's possible. So the kind of things I'm talking about are sending messages that you would never intend to pay for would be one example. So you can kind of do the sort of ding-dong bitch at a doorbell, right? You turn up to a door and knock on it and then run away. And you've annoyed someone by conveniencing them. And in this case, you're asking this node, this service, to do some work. But the service is never going to get compensated for that, which isn't really fair to them, right? So when you're designing how this works, you have to keep in mind the kinds of misbehavior that people could get up to if they wanted to either just troll or possibly attack the system maliciously. Not particularly a concern. It's just something that you want to prevent from being a possibility in the first place. And so this mechanism for payment between the sender and the node needs to be effectively trustless. It needs to not rely on a trust relationship between the sender and the node. And that's part of why this is a trickier problem than it seems. The way that this payment for the service is made is using the blockchain and smart contracts. The rest of this talk is going to be explaining what that means at the highest level that is still useful. That's my goal with it. In the fourth talk, we're going to get into exactly how this works and hopefully satisfy some of those detailed questions. But for today, I'm hoping that we come out of this knowing what the moving parts are for, even if we don't necessarily know how they work or why they work in particular. So that's the key point, is that this incentivizing of the node is done using the blockchain and using smart contracts. If we think about the effect that this has, if nodes are now paid for providing the service, this is our trade-off from before with no incentives. So the node is essentially donating their time to do this, and their only motives are these altruistic, selfless ideas. If we go to the incentivized version, we now have this other reason to provide the service, which is the service rewards, right? The compensation from the sender. And you can see that that tips the scale to this side for a lot more people. The end result of that is that a lot more people are going to be interested in providing this service. And that means that the network can scale and provide private decentralized comms to a lot more people than unincentivized systems. So that's the overarching point of this incentive stuff, is we want more people to run these and be able to provide this decentralized infrastructure backbone for messaging. And the nice thing about this structure, where the sender pays the node as work is performed, is that if the demand goes up, the node or the service provider has to do more work. So the costs of providing the service go up, but also so do the benefits. And so this system has this nice symmetry where the more work you're doing, actually the better it is for the node. So scaling isn't an issue anymore. It becomes more about technical constraints, which you can solve, rather than fundamental, who's willing to do this constraints from an altruistic, selfless kind of voluntary system. So this is essentially a recipe for mainstream private comms. And I think that's the key point, is that if you can solve scaling like this, you are onto a winner. So now we're going to get into the how a little bit. So if we come back to this slide, there's this blockchain section here, which is what sort of handles the incentivization. It's sort of the thing that does the payments. But this is a concept that's quite complicated and often misunderstood or explained in strange ways. And I think that it's worth going into exactly what's involved, or sort of the properties of the blockchain that we care about for this, just setting those out. And then giving a little example of a smart contract, which would actually do the incentivizing, so that you can get an intuitive feel of the kind of thing that we're building, with more detail on exactly what we're building coming in the fourth talk. A blockchain is essentially a public and tamper-proof record of events. So it's just a list of things that happened, one after the other in time. And because it's tamper-proof, it's a really good way to store information that people would like to tamper with. For example, whether or not a particular transaction, movement of funds from one place to another, if you could remove that from the list of things that happened, you would have more money, right? So people have a strong incentive to lie about that sort of thing. Because it's tamper-proof, that's why you can do things like tokens and decentralized finance and all that sort of stuff on a blockchain. For similar reasons, it's also good at recording ownership of things. Exactly why it's tamper-proof is a talk of its own, so we're not going to go into that. But I think if you can understand that it is, that there's no way for people to change what it says in a cheating kind of way and lie about what's happened, then you sort of get the essence of this that we need. And then built on top of the blockchain, or sort of an extension to that idea, is this concept of a smart contract. And these are really misunderstood. And so I'm going to take a second to explain some things that these are not. So smart contracts are not digital contracts. So say, I don't know, like a tenancy agreement, I go and digitally sign something, right? That is not a smart contract. That's just a file with my signature in it. So we're talking about something different. Smart contracts are essentially computer programs that run on the blockchain. So so some computation is done, and then information is written to the blockchain as a result, as like a new thing that happened. So this means that you can do things like logic, so like an if statement. If my wallet contains more than 10 ETH, then do this, otherwise do that, right? You can start to put conditional reasoning, and you can do all of the things that you can do with code, but you can do them with information, quantities, and events that are stored on the blockchain. And in the same way that the blockchain data is tamper-proof, like no one can lie and replace that information, the execution of this code is also tamper-proof. So people can't lie about the result of it and put that on chain. And the code will run exactly as designed. It could still be buggy, like they could design it wrong, but once it's there, it will faithfully execute the way that it was intended, or the way it was written down in programming terms. So you can't lie about the outcome of a smart contract and include that on the blockchain. They always work as expected. And that means that you can use the logic of a smart contract to build something that feels similar to a legal contract in real life. So a legal contract in real life is an agreement between two people about what each of them will do in certain situations, or like the outcome of the future. So you might think of a very simple legal contract as, a very informal one, for example, would be betting on a coin toss. Two people come forward with $10 and you flip a coin, someone calls it, and whoever wins walks away with $20. You could write that up formally as a legal contract and then enforce that contract through the court system. The difference is with a smart contract, rather than using the courts to make sure that the outcomes happen, the code of the smart contract can write the outcomes to the chain, and so cause the outcome to happen based on the logic of that code. So it's sort of enforcing its own outcomes. It doesn't require a legal system to back them up. And that's the primary difference between a legal contract and a smart contract. So we can talk about these in a bit more specific detail. We're going to use that coin toss example. So if you imagine writing code for the contract, it might be something like this. Step one would be collect the funds from both players. So two other people would send in 0.1 ETH into the contract. And then once the money's there, the contract would run and generate a random number. So that random number is effectively the coin toss. And based on what that random number is, the smart contract can figure out who won, player one or player two. And then once that coin toss happens, the smart contract itself sends the 0.2 ETH from both people to the winner. That's a very simple implementation of something that you might be able to write a legal contract for. So it sort of shows that parallel. And one of the really interesting properties of this is that in real life, if you bet $20 with someone on a coin flip, you're not actually guaranteed to get the money because it's still in their hand. They could just walk away, right? The enforcement of that comes down to trusting the other person to actually uphold their end of the deal. But because the smart contract takes custody of the funds in advance, as soon as the players send their funds, it's out of their control. And the only thing that determines the outcome is the logic of this code in the middle. So you end up with this situation where smart contracts can trustlessly enforce a set of rules. In this case, it's the rules of the coin flip. And that ends up being really useful. If we take that as an example, it's not too much of a stretch to see that you might use this to write an incentive system that works in that same trustless way. So the players, in this case, the service providers or the operators of this network, would voluntarily join in. They would stake and get involved in this system. And then as soon as they've done that, the outcomes that happen are determined entirely by the logic of that incentive system and how those nodes actually perform. So if you measure the performance of the service providers, then the smart contract can sort of arbitrate and make sure that the right outcomes happen in terms of the incentives, rewarding, good performance and providing a reason for nodes to be careful about bad performance. And there's nobody that you need to trust in order for that outcome to happen. It's just automatic and safe because of how smart contracts and the blockchain work. So that's a lot to take in. What I'm hoping we come away with today is that incentives are really important if you want decentralized comms to scale well. That's the key problem this is solving. And you can do that by making the benefits to service providers outweigh the costs. The way that we actually achieve that is using smart contracts to create the rules of a game that all of the participants are playing. And because of the nature of smart contracts and the blockchain, you can trust that those rules will be fair to everybody and behave exactly as they've been described. And that's sort of the unique aspect of the blockchain and smart contracts, which means they're so important to this project. There's that problem of trustlessly paying the node for work, which we're solving using something called probabilistic micropayments. There's allocating work to each service provider in a way that incentivizes them to participate well and do a good job. And then there's also stuff to do with measuring the performance of the nodes when they're providing that service, and using that measurement to incentivize good performance.
Thanks very much for watching. If you enjoy this content, smash that like button, hit subscribe, and maybe consider watching one of my other videos. Bunnies up!